All right, our final Gilbreth lecturer today is Dr. Xiwen Gong. She is an assistant professor of chemical engineering at the University of Michigan, where she conducts research on next-generation solution-processed semiconductor materials. She earned her doctorate in electrical and computer engineering from the University of Toronto. Xiwen is going to give us an overview of new electronic materials for a more sustainable future. Please join me in welcoming Xiwen to the stage.
All right, good afternoon.
Good afternoon.
I also want to say hi to our students from Detroit. Warm greetings to you from California. So I want to ask you to imagine one day, just one day without any electronic devices. What's your life would be like? It's very hard, right? The reason is our modern life cannot live without electronics because electronics are getting closer to us. So if we think about how we human beings interact with our electronics, such as computer, it's very fascinating to see the evolution. You know, in the past, when we need to input something to our computer, you need to use a punch card. Anybody used punch card before? We have a significant amount of audience that have the knowledge, so our high school students, please do look around. Who raised a hand and asked the question afterwards? All right. So that is a card with holes, and you, I think, slit into the computer, and then they read your information. And that is very hard, and our machine and ourself are so separated from each other. Nowadays, you can just say, hey, Siri, give me some information. You can talk with your computer, you can bring them around, they're more portable, and they're personal. But what about the future? The future of electronics would be even more closely interacted with us. For example, they can directly interface with your skin, they can measure and modulate physiology, such as neuron activity, and they can get the health information in real time, and using those information, you can do diagnosis and even treatment in real time. So that's how the evolution between electronics and us are evolving. We're getting closer. And I really love the theme of this meeting. So we innovate for people and planet. So that trend does not just stop at the electronic and us, but also it is, we can observe that in the, sorry, I cannot click to the, all right, so we also, our world, also harvesting energy in a very, very different way. So electronics plays an important role, particularly in the energy section. You know, solar cells is one of the most abundant resources we have. This is a significant amount of energy that is available to us for free, and it's clean. And the way we harvest solar energy in the past are based on those centralized heavy infrastructures in those remote areas. And, that is very far from where the electricity are actually being used. But now, because of the drop of the price, the manufacturing, the scale up of the solar panel, we can actually afford to have those energy harvesting devices on our rooftop, on top of the parking lot. And that is more distributed and more local. It's closer to the end use of the energy. What about the future? So we're looking at the our energy harvesting devices that are even more lightweighted, and they're more integratable with us. And then we can imagine the future of energy harvesting would be even more personalized and mobile. And so these are the generation, the energy generation is moving closer to the point of use, and the future of electronics is no longer just about making device faster or more efficient. It's also about bringing the technology closer to us and closer to where it is needed. So, but there is a cost, or there are some challenge of bringing electronics closer to us. For example, if we want to have our electronic devices such as your phone, your computer getting more closer to you, to be, let's say, on the part of the body, we face a fundamental challenge. most of the electronic materials are made from materials like silicon and metal, and these are the materials are rigid and very brittle. And our body are very different. Our skin are soft, they're stretchable, they're possibly moving, so they're very dynamic. In fact, silicon is 1,000,000 times stiffer than our body. So imagine if you put a rigid material on top of your body, what's going to happen? When you're moving around, first of all, there's a mechanical mismatch, and then that can lead to stress builds up at the interface, and therefore they could crack, they could peel off from your body, or eventually stop working. So the problem we're facing is clear. These materials that are used for electronic materials today are never designed to live on the body. So if we want electronics to truly integrate with us, the materials themselves has to change. So the question is, what do they need to become? Well, first they must be soft, so that they will be able to bend without cracking, and they have to be stretchable so that when we are moving, for example, the elongation of our skin will not break them. And thirdly, they must be conformal so that they allow them to be curved and then on the dynamic surface such as our body without peeling off. So in the other words, wearable electronics must physically behave almost like skin. And these are very, very tough requirements. And today, most conventional electronic materials fail to meet those requirements. So what are we going to do? Well, one of the very earliest breakthrough in developing those wearable electronics come from what we call the system-level design. And this idea is very elegant, actually. So the idea is we keep the rigid electronic devices component as they are, like those LEDs, and then we put them on soft substrate, such as those plastic substrates, and then we connect them with wires. So if you connect them with these wavy wires that can stretch like springs, then when you stretch them, they can maintain their functionality. And those work are pioneered by John Rogers from Northwestern and has been incredibly impactful. So it indeed enabled the first generation of wearable electronics systems. But as we push for larger scale fabrication or scalable manufacturing, this approach becomes more complex, and it requires assembling many tiny small devices next to each other so precisely on a flexible substrate. So we ask a different question. What if electronic devices materials are soft from the start? So instead of mounting rigid islands on soft substrate, what if we just have the electronic material that are intrinsically soft and stretchable, and we use them to make electronic devices? Wouldn't that solve the problem? So that is pretty much what drove our research. And here I want to show you a video of what are the electronic materials that we make, that they're extremely soft and they can be stretched to 100% of its, actually this particular example, we can stretch it to 3 or 4 times of its size and it's still maintaining functioning. So these are the strategy that we want to explore, which is we want to design material from scratch, electronic material that they are mechanically soft. To demonstrate the idea that whether it works or not, we would like to first look at one example of wearable optoelectronics. Anybody know what is optoelectronics is? Great, all right. For the folks who are new to this term, so optoelectronics is a class of electronic that generate or detect light. For example, your phone, the screen are made of LEDs, the emitting light. Solar cells, they're absorbing light. So these are all optoelectronic materials. And they're incredible because as a wearable technology, when they integrate it on the body, they allow the light to become a non-invasive probe that can detect our health information. How many of you have smartwatch? Majority of you, actually. So smartwatch can measure your heart rate, right? And in the, I think, earlier version of Apple Watch, they can also measure your blood oxygen level. These are very critical parameters, especially during COVID. You want to know your oxygen level. And how do they do that? They actually measure your oxygen level and the heart rate using light. So there are light emission diode on the back side of your smartwatch, and there's a photo detector. So they shine lights to your skin and collect how much of the light bouncing back, and then using some algorithm, they can calculate your heart rate and how much of the blood oxygen is there. So it's quite impressive how light can be used in probing our health. So at its core, wearable optoelectronics is really transform light into a real-time, non-invasive probe to monitor our health, and can even sometimes modulate our health. For example, this is, anybody know what is this for? Yes, this is anti-aging device. And also we can use light to actually treat disease, for example, photodynamic therapy. Sometimes we can even use light to modulate neuron activity. So this is a great platform and then wearable technology, but then the development of the optoelectronics that are wearable and soft is quite challenging. Because look at this, most of the materials and devices we're using today, they are not soft. So we actually need to figure out how to make those conventionally rigid electronics more wearable. So in order to do that, let's first look at what is the challenge. Where is the challenge come from? I want to use one example, which is LED, as a demonstration. So conventionally, well, to simplify, LED is made of a few layers. There are electrodes, there are semiconductors, there are another electrodes, and then the electrodes is in charge of injecting current to the semiconductor, and the semiconductor receives those charges and emitting light. Most of the time, the electrodes are made of metal. Looks like this, all right? And the semiconductors are, highly crystalline material. They look like that. And if you want to make a wearable optoelectronics, you need to make all the component very soft and stretchable. But by the look of those materials, do they look like soft and stretchable to you? No. So what are we going to do? These are the electronic materials we're using today, and they are not soft. So therefore, I want to ask a question. How do we make something that is intrinsically rigid and stiff to something that is soft and potentially wearable? Anybody have idea? Yeah? Make them thin, right? I love the idea. Thank you. So, well, as a bulk, metal as bulk, they're very brittle and rigid. But what if you make them very thin? Particularly, for example, steel is very, very tough and non-conformable. But we know if you make them thin enough, you can make them very soft, such as steel, right? So that is pretty much the idea. How do we make things that are intrinsically rigid to stretchable? It's not always like inventing new materials. Sometimes it's about reimagining what we already have and then create them in a different form. So the idea is if we can turn those electronic material into thin fibers and then let them to make this network, then they can become soft, flexible, compressible, and not losing their electronic property. So that is pretty much the design idea. Instead of steel, we actually, using silver and sometimes as a metal, for example, we sometimes use highly conductive polymer, but then we can make them into wires and then let them to form this interconnected network and then embed them into polymer matrix. So as a result, this final product looks like this. Now you have the electrodes that made of those nanostructured metal that they are both conductive and wearable. So they are very soft and stretchy. So that is fascinating because just changing the form from bulk to a nanowire, which is around 1/4,000 times thinner than your hair, you can actually make conductive material that is also mechanically deformable. So we solved the problem of the electrodes, but how about the semiconductor part? We still need things to emitting light. Long story short, we can also make the semiconductors, in this particular case was the polymer semiconductors, which they're known for emitting light, but then we make a thin fiber of those and then embedded them. This was work from my former advisor, Janan's group. They embedded this into an elastomer matrix, and then look what they achieved. It's incredible. Now you have a polymer LED that can be stretched to 100%. While if you don't do this, if you just use a bulk polymer, they're gonna break at 2-3% of the strain. So that is a very similar strategy to the electrodes, how we modify the semiconductors property to make them to be mechanically deformable. So, well, building on that concept, we also ask, can we actually apply the similar design strategy to even better light emitters, such as quantum dots? So what is quantum dots? Anybody have heard about that? Okay, great, right? For our younger engineers who have not heard about this, these are the colloidal quantum dots with a very, very small size. These are semiconductors with a size of a few nanometers, and that is this amount of smaller than a cubic of ice. And what is incredible about them is they are great emitters. So this is an example that the quantum dots we synthesize in the lab, if you put them under UV light, you can see they're extremely bright. And their color of emission can be tuned simply and continuously by changing their size due to the quantum confinement effect. So this is a very incredible class of emitter. But the problem is, you know, if you want to make them into wearable form, they're not very stretchable. So if you deposit a thin film of quantum dots and if you apply a tiny of strain, they're gonna break. So we applied the design strategy explained earlier. We embed those colloidal quantum dots into polymer matrix, but in this case, we're using semiconducting polymer matrix, which they're good actually not only deformable, but also transport electrons. So now we can have this incredibly stretchable quantum dot-based LED, where this is just the photoluminescence, so they emit light under UV light, but this is also the very first quantum dot LED that can be stretched to twice of its size. What does that mean is you can imagine you're stretching your phone twice of its size and it still display the image. Do not do that now because you will break your phone. So that is, the very interesting results we got. We also we demonstrate that with this technology, you can have the skin interface display in the future, but also you can use this as a probe for your health, for example, similar to Apple Watch. All right, so we have talked a lot about how electronics are moving closer to us. They become softer, they become wearable, they are more bio-integrated, but that's not the end of the story. Electronic moving closer to us, energy has also moving closer to us too. So how do we, for example, convert energy initially from very far to closer to us to right now on us? Is it possible we can actually now harvesting energy in a way of the wearable electronics, and why that is helpful? So I'm going to spend the next 2 minutes talking about this. So first off, I want to introduce you a very interesting technology in energy harvesting, which is the perovskite solar cell. They are perfectly suited for this purpose of getting energy conversion closer to us. They are processed from a solution, and then that is very different from our current technology, which is silicon. They actually need a lot of energy to melt, to purify your material, but this material is kind of magical. You can just put some salt in a solution, cast them into a film, then you can have your solar cell. They can be made onto very light substrate, lightweight substrate. For example, here is a polymer substrate, and they can already achieve very high efficiency. In our lab, we can achieve 24%, but around the world, it's anywhere between 24 to 27, which is incredibly high for a single junction cell. This opens the door to flexible and wearable energy harvesting, and that can be used in a lot of scenarios, which I will explain one in in detail later on. So compared to other technology, this perovskite solar cell technology is extremely efficient, but most powerful aspect of it is it has highest power density. So it can generate most of the amount of power with the least amount of material that you're using. So, and they are actually flexible and deformable. So that's why, this new technology is really just ideal for mobile and deformable energy harvesting. So in our group, we focused on not only making them more efficient, but also improve their stability. And we have continued to work on this. But I want to, towards the end, I want to show you why this new class of thin film solar technology can help us more than the conventional solar photovoltaic technology. Imagine you are hiking in Death Valley. Anybody have been there? Oh, a lot of you. Okay, so these are one of the remote and unforgiving landscape in the US. And if somebody got missing, drones are become an essential tool to do the search and the rescue, especially in those areas actually you cannot access to vehicles. And most of the commercial drones today can only fly from 20 to 40 minutes, and that covers this area this small. And they have to go back and then swap the battery. So, but sometimes, that's not enough, and then that limits their effective range. And then, but if we can extend them from today's 20 minutes to 3 hours, look how much more area we can cover. And that could mean, life and death in some of the occasions. So we have interviewed some of the folks from the Department of the Interior, and they said if you can make the battery, if you can solve this battery problem in drone, you are making a huge difference in this field. So that's why we think right now our group at the University of Michigan is working on this idea to have the flexible and deformable perovskite solar cell to be attached to a drone to power them. And through our calculation, you can actually increase the drone flight time by 40%. And it can only be done through this technology, because if you put a silicon or other sort of solar cell, because they're so heavy, you are not going to gain much of the flight time. So that's how incredibly unique this technology is, and I do believe that's going to change the energy harvesting in the aviation a lot in the future. So as energy and electronics continue to evolve, we are no longer just solely aiming for better performance. We are designing technology that can move closer to us and also better to the world around us. So with that, I would be happy to take any questions.
Very impressive. Thank you so much, Xiwen. I think we have time for a couple of questions. Down here in the front, and then maybe one up there. Thank you. Yeah, thanks for your patience. Please. Yeah, really impressive.
Thank you.
I think maybe they're going first.
Hello, my name is Miravan Vyahe and I'm from Cabrillo High School. And my question is, when in the future do you think the public will be able to purchase and use these devices, and what are the costs looking like?
That's a great question. So right now, a lot of the wearable electronic devices are in the stage of research and development. And then in order to bring them to the market, there are a few challenges we need to address, such as their durability and their scalability. And the cost eventually would also need to think about that. But right now, a lot of the device, we can make them work at a small scale, like a very tiny, on a tiny substrate. But when we scale up, we're still facing some challenge. So I would imagine, also depending on the technology, for example, perovskite solar cell technology right now is having a lot of attention. I would say in the next 2-3 years, we should see not a wearable version, but a rigid version of perovskite hitting to the market. There has been a lot of tests there. On the wearable one, we need to figure out the durability issue, and that could take another few years. So yeah, great question.
Hello. I'm Alexander Chia. I'm from Cabrillo High School. And my question for you is, how does changing the scale of these electronics affect its original purpose slash performance, and maybe even its lifespan too?
That's a great question. So first of all, we're changing the form of electronics from rigid to wearable with the goal of to help them better interact with our body so that they can get information more accurately from the body. So then we went through a lot of strategy to reinvent the electronic material, but that come at a cost. So I would say compared to our rigid electronic material counterparts, most of our soft electronics performance is not as good. And the gap is getting smaller, but there's still a lot of space to improve. So on that point, I do think as a community, we need to work on that to increase the soft electronics performance, including durability particularly. What's the second part of the question?
How does it affect the lifespan?
Yes, I think I just mentioned that the lifespan is significantly lower than the rigid counterpart today. Yes.
All right, thank you so much, Xiwen. Very impressive.